Let's get started again, everyone. So welcome back for the second part of this session on in-context learning.
Welcome back, everyone. Thank you for coming back. I hope you're refreshed despite the short break. So my name is Amal, and I'm going to talk to you today about distributional properties that in the data that can impact in-context learning emergence. So this is not something I'm actively working on, but it's something I'm generally interested in. And we discovered this line of works actually when we were looking at online learning with transformers in a supervised setting. Jorg will say a few more words on that later. So let's start by resetting up the problem. In general, here we're interested in two modes that exist in neural networks, the in-weight learning and in-context learning. So generally, in-weight learning is slow, gradient-based, and typically needs large corpora of data. This is what we can see generally in standard supervised learning using datasets like ImageNet, and we can talk about in-weight memorization in this case, for example. In-context learning, in the other side, typically doesn't require gradient updates and is thought of as a way of adapting rapidly to a few examples. It's usually before the era of transformers, not always, as what Razvan mentioned. It usually happens when we explicitly meta-train for it. But we've also seen that in recent years, there is an emergence of this capability in large language models and vision language models, even when they are not trained specifically for it. And this generated a lot of interest, which is even more important or interesting is that in these models, in-weight learning and in-context learning also actually happen together. So the question we try to answer here is why? And there are multiple hypotheses. We've seen the talk by Johannes looking at mechanistic interpretability. We can think in general that transformers can have some kind of special property or inductive bias that is actually interesting or can be helpful for emergence of few-shot learning. The hypothesis that we're looking at here is actually the data itself. And the thing or the property that exists in naturalistic data, similarly to language, so something like, for example, the fact that data is long-tailed. We know that language actually follow this power law distribution, or that language is bursty, in the meaning that words in the language tend to appear clustered in time. So, for example, nowadays we can hear a lot of talk and news articles about the Olympics. This will disappear in a couple of months and will occur again in 4 years, maybe. And actually, maybe the idea here is that maybe these properties are behind the emergence of in-context learning. Or also, maybe another point of view is that maybe language is interpolating between these two modes of learning, the supervised way where we see actually items reoccurring, where we see labels and input mapping that are fixed, and the few-shot meta-learning where actually we explicitly give the modeling training sequences that resemble to what we wanted to handle, where typically items and labels are actually context-dependent. Language is actually in between these two. We can find a part of it that is recurrent, a part of it that is somewhat fixed. We can think, for example, about technical words. We can also see, on the other hand, rare words that rarely reoccur or happen again or are seen again. And these many-to-many relationships, words that have different meanings in different contexts, for example. So yeah, what I'm going to present here is actually a couple of papers that are looking at distributional properties that are, inspired from this naturalistic data characteristics, and also another work that looks at the property of in-context learning before I give the floor to Jorg later. Okay, so let's start with the first paper. In this paper, the authors actually studied this hypothesis of the impact of certain types of non-uniformity in the data on the emergence of in-context learning. And actually, they also show that this doesn't hold only for language, but also for other types of data. To study that, they actually modify standard few-shot learning dataset, which is omniglot, in a way to control the distributional properties of the data And then after that, measure the effect on few-shot learning and in-weight learning. There are multiple implications for this work, but one interesting implication is that beyond understanding the behavior and performance of large language models, it gives us directives on how we should design data sets and collect them in a way to encourage these kind of behaviors for other modalities as well. So in general, experiments conducted with a causal transformer. The transformer sees sequences of image and labels pairs, and it's giving context first and then a query, and is trained to actually minimize the loss of the prediction giving this query. So nothing special here. This is what Johannes presented earlier. The training data is example of training data, a sequence. It's handwritten characters with labels. This is particularly an example of what you call a bursty sequence, meaning that we see examples and classes repeating in the context, and the query is one of these repeated classes. And the other property here is that, contrarily to what we saw about few-shot learning, the mapping between examples and labels is fixed during training, which means that the model can solve this prediction problem in two ways. It can actually learn in weight, given that these mappings are repeated over the training data set, but can also learn in context by adapting to the context it sees. So given that we have these two strategies of learning, the evaluation actually looks at them separately. In the first case, to study in context learning, the model is giving something very similar to what we see in typical few-shot learning scenarios. So it's composed of a sequence of two held out classes that are not seen during training, repeated in context with random labeling 0 and 1. And then it's given a query that is one of these two classes. To evaluate the in-weight learning of the model or the in-weight memorization, well, the model sees a bunch of sequences in training, and it's actually tested on one of these sequences where actually the query is not seen in context at all. So the model needs to rely on the information that is already stored in weights to be able to solve it. So with that, the authors set up for an exploration, and this is the first set of results that they saw. The first important characteristic they observed is burstiness in the data. So you can see here, an example of bursty and non-bursty data, and they control the proportion of these types of sequences in the training data. And we can see in this graph here, in the right hand, that actually in context learning is getting better as the data gets more bursty. On the other hand, we can see that in-weight learning is getting worse. So the model is less able to memorize the data when it's more bursty. The other interesting observation is that in context learning, when we continue to train, tends to fade, giving way contrarily to in-weight learning. So I think that in context fades and gives way to in-weight learning. I'll say a bit more about that later. Another important factor in the data that is important for the emergence of ICL is scale. What we mean by scale here is specifically the number of classes that are observed in the training data. And we see that the higher the number of classes, the better is in context learning, but also we see a similar trade-off with in-weight learning here. Finally, in this first part of results, the authors looked at other characteristics of naturalistic data, more particularly related to this dynamic meaning that I mentioned earlier. So they studied two settings, either multiplicity of item label mapping, so one item, multiple labels, but also within class variations. And in both cases, we see that more variation leads to better in-context learning. So far in this set of experiments, the authors in this paper looked at in-context learning or in-memory, in-weight learning separately. But they do coexist in large language models, as we said, and it's important that they do. So what type of properties in the distribution that are needed for this to happen. So interestingly, the authors observed that when we have skewed distribution that are power law-like, Zipfian distribution, similarly to what we can see in language, as you see in the left, actually, these two kind of learning can coexist, and particularly when they varied actually the skewness of the Zipfian distribution, they found a sweet spot when they can both coexist at an exponent of 1. So this actually also intriguingly corresponds to what we observe in certain natural language corpora like English. Actually an intuition behind that is that with this kind of distribution, the common classes, the classes that are more frequent, are seen often enough for the ways to memorize them, but also the rare classes in the long tail actually are helpful to make the in-context learning appear. So yeah, we talked about data so far, but another observation in the paper is that architecture does matter. So when they conducted the experiments with other architectures like RNNs and LSTMs, they didn't observe at all the same in-context learning emergence. It doesn't mean that these models aren't capable of such learning, but just in this particular setting, it didn't happen, which means that looking at architecture alone doesn't lead us to understanding what's happening, and looking at data alone doesn't do that as well, so we need to look at both of them together. We need the right data for the right architecture. So to conclude on this first paper, we've seen that certain distribution characteristics of the training data actually help promoting in-context learning. Interestingly, these features are actually present in language and naturalistic data. And we've seen also a trade-off between in-context and in-weight learning. But that both of them can be achieved with the particular type of distribution. We've also seen that architecture is not the only way to explain all that. It is important, but insufficient. In other words, attention is not all you need. The scale is also not all you need. And it's actually an invitation to consider more the non-uniformity in the data. The world is naturally non-uniform, and I think I don't need to convince this audience about that. But also, this non-uniformity is not only a challenge, it's also an opportunity because it leads to emerging of interesting capabilities like in-context learning. And this opportunity is even more interesting with the fact that non-uniformity is not only in language, but it's actually universal and observed in other types of data like biology, like music, like physics, and like, interestingly, the experiences that we experience in early childhood as well. So there is a lot to do there, and it's interesting to study further this kind of interaction between data and models. So now I'm moving to another one, but maybe it's actually a good time to stop to ask a question. Questions? Yeah, go ahead, please. Yeah. Mm. Well, I don't really remember that point, but actually, yeah, I think actually, the point of these experiments is that they try to actually try similar, I mean, different architectures with similar settings exactly on the same data, and it didn't emerge. So actually considering, I mean, what you said is also part of playing with the architecture. So we need to understand how these, play together. Yeah. Yes, please. Maybe Johannes would be better to answer that. Yeah. Yes. Yeah. Yeah. Actually, what it means here, the more bursty data we have in training, the lower is actually the accuracy you can obtain with in-weight learning. No, that's actually, we vary this proportion in training. Yeah. Okay, let's move for the sake of time. I don't know how we are doing in terms of time, actually. Okay, so I'll try to go quickly over this part. So yeah, in this work, actually, the authors look at still look at certain properties in the data distribution, but a slightly different one. They look at the notion of diversity. And in order to study that, they focus on toys setup with the regression tasks. But the reason for that is that in this setting, we can actually derive a notion of tasks, a space of tasks in a rigorous way, a notion of metrics in this space that, tell us how different a task is from a given set of tasks. But also it can, give us a way to actually parametrically vary this diversity and to derive optimal Bayesian estimators for given different priors. So with that, actually, the idea is to compare transformers trained on variable diversity sets and see study the capability or the emergence of in-context learning by comparing that to these different Bayesian estimators. And actually, they managed to identify a threshold after which in-context learning appears. And this actually cannot be explained by Bayesian learning perspective. Okay, so for just quickly a definition of task here. So task is, basically described by the weight vector W here. There is a randomly generated from a Gaussian distribution. And the transformer is given actually a sequence of input-output pairs. The inputs are also randomly generated, and the outputs correspond to actually the correct labels with this model here. And given a sequence, the transformer gives k outputs taken into account in context, actually, all the observations up to the point and the point that we are looking at as query. And yeah, so this is how it works, also fairly standard. So yeah, going back to what I said, typically our pre-training data set is discrete set of tasks composed of m tasks, as you can see here. And if we actually the optimal base of estimator on this empirical distribution is given by this discrete minimum mean square error estimator. And conceptually, a pre-trained transformer that minimizes the loss that you see here with this distribution should behave similarly in the sense that it should produce similar outputs. On the other hand, what we are looking at is actually the capability of generalizing to new tasks. So what we want is to actually achieve a low loss with this true distribution here. And the optimal base of estimator in this case is the ridge estimator that you see here. So also what we want here, if a pre-trained transformer actually is able to optimally perform on new tasks, it should behave similarly to this estimator. With this in mind, the authors pre-train a set of transformers on a pre-training data set with a variable degree of diversity M. And they compare at each time to either the minimum mean square estimator or the ridge estimator. And that taken into account either the pre-training distribution or the true distribution that we're looking at. And this is what they observed. In the first set of experiments, they saw that actually when we increase the number of tasks, we first see a behavior that is close to the mean square estimator training data set and also on the held out tasks. But as we progress, actually the pre-trained transformer gets closer to the ridge estimator. At the expense is that actually also both on the two data sets, so which means that it gets better at actually estimating new tasks or performing on new tasks, but the cost that we pay is that it's losing performance on the pre-training data set itself. And this transition happens at the task threshold here. So this is interesting because it's actually what happens here after this transition cannot be explained with the Bayesian learning dynamics, because actually here we are still learning on a discrete set of tasks, even though it's a large tasks, but even with that, the pre-trained transformer actually breaks out of this regime and even perform better than it. A question that they asked in the paper is that actually related to the number of data points that are seen per task? So they scale this number either by playing on the batch size or the number of training steps. And what they observed is that at the small number of task regime, we can see that increasing the batch size actually makes it closer to the Bayesian estimator. While after the threshold, it's reversed, and the behavior, there is a transition phase actually happening at exactly this same threshold that we've seen before, meaning that the batch size is not impacting the threshold of transition. This is also the same when we increase the number of steps. But what does impact the threshold is the dimension of the task itself. So when they increase the dimension of the problem, which means the dimension of X and Y, they actually observe that the threshold at which the transition happens is increasing mildly. And the interesting observation confirming all what you've seen before is that the pre-trained transformer actually scales way better than the Bayesian estimator here. Yeah, so to conclude here, the authors observed an algorithmic phase transition in the pre-trained transformer from the minimum square estimator to the ridge estimator that happens at an intermediary threshold, that this scales moderately with dimension. It doesn't depend on the scale of the dataset itself. So scale alone does not lead to good in-context learning performance, according to this study. The open question here is that this is a pretty toyish setup. So how much of that actually carry over to language and vision tasks, or general other types of tasks? So this is an open question. I still have a few slides more. I'll go through them quickly. It's not particularly related to the distribution characteristics of the data, but it's an interesting phenomena that has been observed, and I think it sets up also the talk for Jorg later. And this is actually was mentioned earlier, is the characteristic of transience in context learning. So in this work, the authors observed that in context learning is transient across setting, actually meaning that if you continue to train, even on data distribution that has been shown to incentivize in context learning, building on the work that I started with, it's actually kind of fades away. And it's actually a word of caution against overtraining transformers trend that we are seeing now. Because decreasing training loss doesn't necessarily mean that the capabilities that we are observing, like in context learning, are persistent. So yeah, basically it builds on the same setup that we've seen in the first paper, but the idea is to train on data that can be solved at 100% accuracy, either by in-context learning or in-weight learning, while we test on data that is either solvable only by ICL, as you see here, or only by in-context learning, as you see here. And with that, they show that when we overtrain the transformer, we see that the loss continue to decrease, and in context or in weight learning accuracy continues to increase. All in the same time, in context learning first increase, but then decreases. And that this is actually persistent when we vary several things, either depth of transformer, the scanning of dataset, the way we actually encode the images to go into the model, or the skewness of the distribution. And showing actually when we vary that, we can mitigate to a certain extent the transience of in-context learning without completely removing it. One good news in the paper is that simple intervention like regularization or L2 regularization in that case, particularly in the MLP parts of the transformer, actually helps to remove the transients completely, at least in this setup of simulation. And they also observed that when we increase the width of the model, in context learning, transience actually improves a little bit, but the capability itself, as you see here, is not increasing. In weight learning, on the other hand, can get slightly better. So this suggests that this transience is a result of the tension that happens in the model between in-context learning and in-weight learning. So yeah, the conclusion here is that in-context learning is not necessarily persistent. We need to pay more attention to that. Probably it's an invitation to also monitor that while training, in addition to the training loss. But there are a bunch of open questions here. Basically, how we can understand better in context learning and in weight learning, how we can make them happen simultaneously, not only in this emergence phase, but also asymptotically. Yeah, so that brings me to the end of this part of the talk. A few of the key takeaways here is that data distributions or properties of data distribution are key or seem to be key for in-context learning emergence. Things like burstiness, scale, dynamic meanings, diversity, all of that matter. But also there are other aspects that can impact that, like architecture, like regularization, like the number of training steps, etc. But at the same time, this in-context learning seems to be a transient phenomena, which calls for a better analysis and understanding of its interaction with in-weight learning. And with that, I'll invite Jorg to continue. Unless maybe you have a few questions first. Yes? Post-training, sorry, I didn't hear you. That's interesting. Well, it's not something that these papers looked at, but it's an interesting thing to consider. It's actually, I think also Johannes mentioned that earlier. Actually, continue to fine-tune is, understanding how fine-tuning further impacting context learning is important to study for sure. Yeah.
Maybe I have a point. Like from personal experience, I tried comparing fine-tuned and non-fine-tuned models, and the in-context capabilities, that was not a clear signal. Like it was really more or less random for the current techniques of instruction fine-tuning. I guess I'm in the lucky situation I can overrun as much as I want, and it would be very impolite if you leave. No, I would. Okay, so I just want to very quickly mention two papers, and that actually refers a bit to what you just asked. So this is different in the sense that what Amal just described are the distributional properties of pre-training and how that affects the basic capabilities. There are two papers that propose something that's probably quite intuitive, I would say, in retrospect. That's just saying you take your pre-trained model and then fine-tune it on on in-context data sets, basically. Like you specifically train it to do in-context tasks. So there are two papers. They both show mild but consistent improvements from doing that for further downstream tasks that are out of distribution relative to this fine-tuning step. I guess that's not really surprising. What is maybe interesting is that the gain from that is relatively modest, but consistent. Curiously, they have not been picked up as much as maybe one would think. I'm not sure why that is. All right. I want to talk about something, maybe changing the perspective a bit. And this is almost a brutal change of perspective. So bear with me. I have to kind of step back and change and maybe reflect for a moment of how we currently think about statistical machine learning. And maybe that explains something of what in-context learning might be able to do. I'm not so sure if that's currently happening already, but yeah, bear with me. There's a few papers I want to point out. So just to really step back and think about what we are currently doing. So most of the statistical machine learning we are currently doing like lives on this distributional assumption. There's a distribution out there, the empirical distribution that's responsible for the data that we are observing. We have a sample set from it. We train on a training subset. Then we have a validation subset to do hyperparameter selection and so on and so on. And then eventually, the framework of empirical risk minimization gives us certain guarantees that we can expect similar performance on further held out data from the same distribution. I guess in continual learning already, this assumption is a bit of a challenging assumption. There is a whole lot of theory out there, actually, which is not very visible, I would say, especially in deep learning. That is, how could we actually do machine learning on a single, potentially non-distributional sequence of observations? Like if I give you this sequence of symbols, for example, simply, I guess we all can continue it in a certain way. And we can't continue it necessarily because there's a distribution underlying each of these digits. We just see a single sequence of observations. And how do we do machine learning in that scenario? Like even the simple task of finding a validation set is obviously not trivial, because I can't really assume that there's an underlying distribution here. The framework I want to talk about is not only for deterministic sequences, but this framework has been discussed also if the sequence is stochastic. However, you can't be sure about that. Like you simply don't know what's the underlying mechanism. Curiously enough, there's been a lot of discussion, of course, how can we do any kind of inference in these non-stationary single sequence scenarios? And much of that goes back to philosophy, and there have been like very high-level principles being discussed, like, for example, oh, if you have multiple hypotheses, what might generate this data? You might want to keep them all around. You want some form of Occam's razor. You want to keep the simpler, maybe upweight the simpler hypotheses to a certain degree. And then, of course, we use probably like Bayesian statistics to update our belief about these hypotheses as we see more data. So the question is, can you create a prediction system or learning system out of these principles? And it's kind of, so there is a formal theory of inductive inference by Solomonov, which is maybe not so well known, which basically shows, yes, actually these problems are solvable, but unfortunately with a tool set that's maybe not very intuitive for statistical machine learners. So the idea is, so this is all grounded in Turing machines instead of probabilistic models. So the idea is you take an infinite number of Turing machines and feed them with random programs, or to be precise, with all possible programs that you can create for these machines. And you assign a weight to each of these machines that's simply proportional to 2 to the power of minus its program length. So more longer programs have a lower weight, and shorter programs have a higher weight. And then all these Turing machines generate sequences, generate output when you run them. And as you observe data, you simply cross out those machines that are incompatible with the observations. So at each point, while you make observations, basically you cross out a whole bunch of these machines. And to make a prediction for the next symbol, you simply weigh all the predictions of the machines that are left over according to their weight, and that's your prediction. That's called Solomonov induction. And there's actually a whole like solid theory about how to think about these individual sequences behind it. I don't want to go into it. Like the pointer here is algorithmic information theory that pretty much works without assuming a distribution that is the source of the data. So long story short, I don't want to go into this too much, but what is interesting that you can show for Solomonov induction is that for every possible sequence, actually this will find the right program that generates more of the data. Like it will make a finite amount of errors, prediction errors, as it sees more data. And the number of prediction errors it's making is related or is bounded by the complexity of the actual data generating process. So if the true mechanism that creates this data is very complex, then it might make many mistakes. If it's a simple process, then it will make only a few mistakes. But in this case, there's no neural network in there. It's the, oh, that's okay. The noise might be data, but it's noiseless because what you measure is, yeah. Like if there's noise in your data, what you would think your model is actually predicting the underlying mechanism plus the noise. It's also modeling the noise as exceptions, so to say. So, of course, working with these Turing machines is something that's probably not very convenient. But luckily, there is a mapping and we can bring it back actually to statistical machine learning. And where I want to go with this is that what we are doing when we are training transformers is we are almost following exactly the recipe that we would follow if we wanted to train models for the single sequence scenario. So it's not exactly the same thing, but transformers, or not only transformers, in context learning and sequence modeling resembles much of the recipe that you would choose if you want to operate in this regime. So, and that poses maybe the question if transformers can generalize beyond even distribution limits, because this doesn't assume a distribution. This could operate on a infinite counting sequence and you would expect it to work. So we know, of course, that compression and log loss are basically the same thing. Whenever I have a probability distribution or model that predicts symbols, that also means I can implement a compression algorithm with the help of that model. That's a well-known Kraft-Macmillan inequality. And so in the following, I will just say D is just a concrete sequence of observations that our model is making. And in this case, like in language modeling, I assume the symbols we are observing and we are predicting are the same. We're just predicting tokens in a sequence. And we know that if we have a model M, whatever that model is, if it can predict the whole sequence with a certain probability, that we could also build a compressor out of it that can compress the data D with the help of this model into minus log many bits, what to say. Right. So that's what already the Turing machine is doing. The more general case, of course, is so we want to model some data D with the machine M, with the model M. And what this framework suggests what we should do is we should find the model M that its own description plus the description of the data with the help of the model together leads to a short compression of whatever data we have. You give me a sequence of symbols, and the goal is to find a model where the model description itself is plus the description of the data with the help of the model together is as short as possible. In reality, of course, typically we want parametric models. So what we want is that the data described with the model itself is depending on some parameter theta. In classical minimum description length, you would do that as you first send over the parameters and then you encode the data with the help of those parameters. But what does it mean to encode the data with the help of the parameters? In practice, that might mean that or the best thing we can probably do is to do this part autoregressively. So we have a sequence of symbols, and we have a model that can use context in whatever way. So the most promising thing to actually get the total likelihood down will be to build an autoaggressive model one way or another. Does it make sense? Do you see basically the relationship here? Does it make sense that there is a relationship between compressing sequences and yeah, having basically autoaggressive models? Historically, pre-transformers, there was actually a whole bunch of literature that did it in a slightly different way, where you would, which is also called the frequential approach, where you would take the sequence of your symbols and then you model basically at each time. This could be gradient, online gradient descent. So at each time when you observe a new symbol, you somehow update your parameters. Can be Bayesian belief updates or online gradient descent. You somehow update the parameters of your model to improve the predictions. We have basically these two different ways. And in context learning in a certain way corresponds to this approach, basically. So is there anything that we can practically do with this? Well, not even sure it's a deep insight with this analogy between single sequence modeling and what transformers do. So there was a quite recent paper where basically the idea was, okay, can we actually simulate Solomonov induction, this mechanism that I mentioned earlier, with a modern transformer architecture? And in this case, they completely took the meta training approach. So what happened here is they actually sampled random programs for a Turing machine, or it was a version of a Turing machine. They would run it for a limited time. We have to get around the halting problem that we never know if it never halts, and generated basically sequences from these programs. And then trained a standard transformer architecture basically on these random generated data sets that were simply sampled to be biased towards low complexity sequences. And after training this model on such a data set, the idea is that basically this model should approximate exactly the Solomonov procedure that I mentioned in the very beginning. It's a model that has learned or has seen that sequences that have a low complexity are more common than sequences that have higher complexity. The result of these experiments were maybe, actually it's kind of quite interesting. So the results of these experiments that the resulting transformers could generalize in certain way out of distribution what they have been trained on. So they have been tasked with different Bayesian inference tasks. And it turns out, even though they have never seen exactly these Bayesian inference tasks, they had at least a positive signal that these models could solve them. So that is, for example, in this scenario. Even though the test data was generated completely out of distribution relative to these. Yeah, I don't want to go into too much detail here. So the idea in this case is simplicity. Even though you are out of distribution, is a certain form of simplicity maybe an appropriate bias to have when being faced with new data? And can a transformer absorb these kinds of biases? So similarly, in this paper also different architectures were evaluated, and they also showed a general improvement in terms of being able to show some of these capabilities, but in general, transformer architecture seem to have better convergence and perform better in these scenarios. It's only a lower bound. Like you typically don't know how short you could compress it. That is the case for these. In this scenario, the test data, that's context tree weighted model, details, and that's a well understood basically space of sequences that can also be perfectly solved with the Bayesian inference scheme. So if you know exactly I will see sequence from this space, I can build an inference mechanism that learns on a single sequence and does optimal prediction. In this case, the optimal prediction is this dashed line. And we actually see that big size transformers actually are base optimal at inferring next tokens. So that's what this line means. So I show you a sequence out of this space of sequences, and the transformer from the very beginning, not only in the tail end, but from the very beginning makes base optimal predictions about the next symbol. Right. So that's when you specifically train a model to do basically to have the simplicity bias. A different paper that looked in this kind of same space of Kolmogorov or of individual sequence inference was basically coming from the other direction. In this case, the idea was we take a standard language model that was pre-trained on a text corpus. And the question was, does this still perform general compression? And in this case, this pre-trained model that was pre-trained on text was evaluated as an image compressor. So the individual pixels actually come in as tokens. Even though it has never seen image data, it would perform very comparably to some image compressors. Yeah, in this case, it's basically if you as we know, compression and prediction are tightly related. So here's, for example, the question when I would use a standard compression algorithm and turn it into a prediction algorithm, how would it complete an image? Versus how does actually a text trained transformer complete an image when you sample from it? Yeah. I don't think there's evidence that this works particularly well, but it works maybe better than you would expect than if you have a simplistic perspective on in-distribution learning. Yes, yes. But it during training, it has never seen images. It is trained on text. So it somehow from the text data inferred that even now these pixel data should be continued in a certain manner. It's on that side, it's maybe noticeable that the image is wider than its high. I guess that might help the visual impression here too. Oh yeah. But they did it in the direction that's longer, so I guess that's easier. Oh yeah. Before, yeah. So I guess there are two things here, and maybe I was too quick mixing them almost together. So in this scenario, we are randomly sampling, or they are randomly sampling programs, use these programs to generate data, and then train on that data. And they observe that this data then generalizes to new data that actually comes from different domains. That was a Lisp style language. So they made sure that all the opening brackets and closed brackets match. And otherwise, there was some pre-sampling. The technical details are in the paper, and I don't know the exact details. Another caveat is that some of these programs might have infinite loops. Well, actually, you don't know if they have infinite loops. You just know after a certain time it didn't generate output. So they limited also the compute per program, which is an approximation. Yeah, so for this paper, there were different generation I should clear out which paper we are talking about. So for this paper, the CTW is a completely different mechanism to generate sequences, which is more like a tree-like Bayesian model, like a state machine almost. Whether or not yeah, it's hard to measure, I guess, in distribution that's a problem in itself. Yes, agreed. Yeah. So in that sense, yeah, it's hard to really measure these things in terms of quantitative metrics, like we had a workshop about that. But it is noticeable that there are ways to think about individual sequences that not necessarily come from a distribution that are generated. Okay, we are running out of time. I'm not sure if I should do this. Let me very quickly mention that one thing we have been recently investigating is basically comparing these two mechanisms. So if we assume that in-context learning allows some limited generalization to next tokens, while at the same time we know that online learning also allows to improve as we see more data. There are possibilities to, of course, basically simply combine these two methods. So we say we are faced with a single sequence of observations, and we model this sequence of observations by at the same time performing in-context prediction, basically the recent history, while also performing gradient steps while going forward. And in that case, again, we can observe, so this is a single sequence of 37 million images in this case. And the task is to predict from each image its geolocation, where the discretized over multiple classes. And what we see here is basically the rolling prediction performance, the accuracy of the next step prediction in the chronological sequence of images. So this is Flickr, Yahoo images, 37 million in chronological order, time-stamped by their by the time they were taken. And we can ask the question of while you do online gradient descent going through the sequence and at the same time doing in-context learning, attending to the recent past, we can ask the question of what happens when you stop gradient updates at certain positions. So for example, after 500,000, after 1 million, after 2 million, and so on and so on, which disentangles the relative contribution of doing gradient updates and relying on context learning alone. I will completely skip this. And I will also skip this. So I guess what I wanted to point out was mostly that we are very used to thinking about distributions as a source of our data. And there's, of course, a whole theoretical framework around it, and it has been very successful. But there is also a theoretical framework to actually think about individual sequences, just sequences of data without even assuming there's an outer distribution that generates these. And if you look at these frameworks and what they suggest, what you should do to do machine learning in that scenario is you should just do next step prediction as good as you can. You do your model selection and the whole machinery as pick the model that minimizes the cumulative loss while you predict one token after the other over the whole sequence that you are faced with. And that these mechanisms have automatically a bias towards simplicity that emerges out of their definition. And that the way how we train model architectures that can do in-context learning actually resembles to some degree these techniques. So I think there's an interesting question here if maybe these can inform future training protocols or future data generation of actually how can we get models that generalize out of distribution. Yes. I didn't get one part. How do you bear with? Mm-hmm. Oh, you would, I guess for these methods, you know how a base optimal algorithm would look like if you know the state space, the size of your state space at least. And in this framework, what you would do, you would compare the cumulative prediction log losses or accuracy, whatever loss you choose, while ingesting data. So what you would do is exactly you measure the log loss per time step. And then at the end of the sequence, you compare the sum of all these losses with the sum of what your transformer architecture would have, has. I think there's the maybe crucial part is that you don't just judge your success how well you do it at the end of training, but you would judge your success by how quickly do you learn as you see these transitions or see your data. Yeah, strict forward evaluation. And I think that's exactly what you are saying. Like if that's what is suggested by these frameworks, that's what you should do to do model selection and to train your models, like care about the cumulative next step loss. It's kind of interesting that the standard training for transformers that we are doing is not so far away because we are also auto-regressively training them, at least within a sequence. Now there's an outer loop that samples these documents, but at least the basic mechanism of auto-regressive modeling in token sequences is very similar to what would be suggested here, namely take the sum of the log losses. That's what you care about. Yeah, I mean, I guess in standard training, we have, in standard LLM training at least, we have these document boundaries and we sample randomly our documents and create batches. This would a bit suggest you would treat everything as one long sequence. You would maybe do cross-attention arbitrarily about cross-document boundaries, but and it would suggest that that's what I wanted actually to point out with this slide. So in standard training, I guess the mental framework is train, and that what we care about is our test set performance at the end, or validation set performance. What this, though, suggests is you shouldn't necessarily look at the test set performance. Maybe you don't even have a test set, but you look at the area under the curve under your training loss when you do single epoch training. So if you do single epoch training, you anyway see new data every time. The sum of these new data losses is exactly the objective that you're supposed to optimize here. So you should value models that train faster in the beginning. So in practice, it's curiously exactly that. So people kind of have learned that that models that train faster in terms of gradient steps also perform better in the end. With caveats, there's like learning rate annealing, and so I think the stated goal is to minimize validation set loss or test set loss. That's what people like aim to minimize. But in practice, because they don't want to train till the end, they look at their training curves and then stop training runs that are not dropping fast enough. And that would be what you should do, actually. You should exactly pick models that train fast in terms of gradient steps. Or not gradient, in terms of observed data. And that would put pressure on models that always generalize basically towards the future. Even if the future is non-stationary, drifting somewhere else. I don't have that here. So, and also we should really stop. So what this suggests, you look at the area under the curve. And if you do that, actually is surprisingly constant. So the noise is in the individual next step training losses. There's a lot of noise. But if you look, unfortunately, oh, wait, yes, do I have it? Wait a second. So this is actually the perfect example almost. So this is in terms of accuracy though. So these are the 37 million images. And what you see on the left-hand side is the rolling average of the prediction accuracy, rolling over 1,000 images, order of 1,000. While on the right-hand side, it shows the average accuracy so far. So you count how many correct predictions made from 0 all the way to 10 million, for example. And then that's the average accuracy. So on the right-hand side, this takes like the whole history into account, which is what you should do according to this framework. And that signal is actually quite stable. And you can also theoretically show that the variance is low. I think we should really stop. Thanks very much.